Hello, and welcome to the video lecture for Topic 8, which will cover conformers, internal rotation, and potential energy diagrams. So, let's start off with conformers. What do we mean when we say that two representations of a molecule are conformers of each other? What we mean is that while the atom connectivity and bond paths have all remained constant, and the distribution of electrons has not changed in that molecule, so these are neither constitutional isomers nor resonance structures, if we conduct a rotation around a single bond within that molecule, we will orient each of the atoms spatially in a slightly different way. And that slightly different way would be called a conformer. So let's take a look at an example. So we'll start off with this molecule. We'll have a carbon atom single bonded to another carbon atom. Off of this carbon, I'm going to put a hydrogen that's in plane with the two carbon atoms. Off of the left-hand carbon, I'm going to put another hydrogen that's in plane with the two carbon atoms. So all four of these atoms, right, the two carbons and the hydrogen, constitute one plane. And so off of this left-hand carbon, I'm going to orient in space using a wedge. So this means that the atom connected to this bond is sticking out of the board towards you, a fluorine atom, and coming behind the board towards me, a chlorine atom. Over on this right-hand carbon, what I'm going to have is coming behind the board towards me, an iodine atom, and sticking out of the board towards you on this wedge, we'll have a bromine atom. And so if I take this right-hand carbon and rotate it around this single bond, so all I'm going to do is just imagine holding this carbon atom in place, grabbing this hydrogen atom, and turning this carbon and the three atoms attached to it like a wheel, I can now draw this exact same molecule, but just in what we call a different conformation. So here now again, I would have my carbon atom, there's my hydrogen, there's my other carbon atom. Remember, I kept this atom stationary and everything attached to it, so I still have a fluorine coming out of the board towards you, and a chlorine coming behind the board towards me. But now, since I've taken this hydrogen atom and rotated it, what I've done is I've placed that hydrogen atom where the bromine is, the iodine atom where the hydrogen is, and the bromine where the iodine is. So let's see what that would look like. Now I have the iodine in plane with the two carbon atoms and the hydrogen atom over here, going out of the board towards you. I now have the hydrogen atom that was up here in plane, and then finally coming behind the board towards me, I would have this bromine atom. So all of my bond paths are the same. All of my electrons are in the same places. All I've done is rotate one atom of this around this single bond, which moves its three substituents. Okay? These would be two conformers of the same molecule. Now, the depiction I have here are what are known as sawhorse projections. So these are both sawhorse projections. And that's just one way that we can show conformers of the same molecule. A much more common way for us to do this is to use what's called a Newman projection. And so now I'm going to generate Newman projections for these two conformers. To start a Newman projection, we draw a circle And then we have to pick a direction to look down the bond we're going to rotate. So again, we're rotating around this carbon-carbon bond. So I'm going to put my perspective, if we were to think of an eye looking down this bond, I'm going to have my perspective be that direction. So that determines that this carbon atom is my front carbon atom. For your front carbon atom, you start with a point at the center of the circle, and then use full lines to draw in your substituents. So I have a hydrogen coming down. Again, if I orient myself as if I'm looking down that bond, the fluorine atom is going out of the board, which would be towards this hand. And so I'm going to put the fluorine over here. And my chlorine is coming behind the board, which would be this hand. So I would put my chlorine here. Now for the second carbon of the bond we're sighting down, we don't explicitly show that bond. It's hidden behind this circle. But we need to still show the 3 substituents, or however many substituents are coming off of it. So in our case here, we have 3. Again, I have this hydrogen coming up. So now instead of drawing a full line starting at that point, I start at the edge of the circle, and I draw a line just coming from the top of the circle out, and that designates that this hydrogen atom is attached to what we would call the back carbon, which is this carbon here, since we're looking this direction down the bond. Now my iodine, right, is coming behind the board towards me. Oh, excuse me. That should be a chlorine atom. So my iodine is coming behind the board on the same side of the molecule as the chlorine atom. And so it would go here. Excuse me. So there would be our iodine, excuse me. And then finally the bromine is going out of the board towards you on the same side of the molecule as the fluorine atom. And so there would be our bromine. This is the Newman projection for this conformation of this molecule. Now we want to draw a Newman projection for the other conformation of our molecule. We start off on the same process. We draw our circle, we put a point at the center to mark this front carbon atom, and the orientation of the 3 atoms connected to that front carbon is the same. We don't need to change anything. We have a fluorine to this side, we have a chlorine to this side, and we have a hydrogen going down. Now notice, since we did this rotation to generate a new conformer, now the iodine on our back carbon takes the place of the hydrogen before. So coming up, I would have an iodine atom. In our new conformer, hydrogen has taken the place of the bromine. So over here now, I would have my hydrogen off the back carbon. And then finally, the bromine has taken place of the iodine. And so now here, I can put my, I can put my bromine atom. Newman projections, what we have here, are going to be the most common way that we represent different conformers of the same molecule. So now that we know how to draw Newman projections to represent different conformers of the same molecules, let's take a moment and look at what different kinds of conformers we can have and what names are associated with those particular orientations of atoms. So I'd like to just, and a really great molecule for us to do this with, the one that I'm going to choose to use is butane. So I'm going to draw one conformation of butane as a sawhorse projection. So we'll have our first carbon connecting to our second carbon, to our third carbon, to our fourth carbon. And now we'll have on carbon 2, one hydrogen out of the board towards you, and one hydrogen coming behind the boards towards me. And similarly on this carbon, one hydrogen out of the board towards you, and one hydrogen behind the board towards me. Let's go ahead and draw a Newman projection looking this direction down this C2-C3 bond. So for our first Newman projection to depict what we've already drawn, we start with our circle representing the front carbon of the bond we're citing and rotating around, and place our substituents where they belong. Full line from the center up for our CH3, full line from the center to one side for our hydrogen, full line from the center to the other side for our other hydrogen. Now our two terminal methyl groups are opposed to each other, so on the back carbon, starting from the edge of the circle going down, I have my other methyl group. From the side going up from the edge of the circle, I have my hydrogen, and from the opposite side going up from the edge of the circle, I have my other hydrogen. So in this situation, we see that the two large substituents, the two methyl groups, are opposing each other, and we call this specific conformation, where we have two bulky groups opposite of each other, the anti-conformation. If we take that back carbon and we rotate it so that this methyl group is aligned with this hydrogen, we can generate a new Newman projection. Again, all the substituents on my front carbon remain in the same place. I have now taken this methyl group, rotating that back carbon around this carbon-carbon single bond. So I'm going to rotate it so that it lines up with the hydrogen over here. And the way I draw that, starting from the edge of the circle coming out, right next to that other hydrogen, I'll put my methyl group. That means this hydrogen has moved to be next to this carbon, or this methyl group, and this hydrogen has been moved now to be next to this hydrogen, this front hydrogen. So even though the bonds in the atoms don't line up perfectly in front of each other, this representation allows us to see everything, and it implies that, for example, this carbon-hydrogen bond is perfectly aligned with this carbon-carbon bond, and that this hydrogen is directly in front of this methyl group if we were to draw a sawhorse projection. This type of orientation, or this type of conformation, similar to what we have here, also has a very specific name. For my purposes, I would like you to refer to this as an eclipsed conformation, right? We have a bulky group eclipsed by a not so bulky group, right? Or a small group, a hydrogen. The technical name for this conformation, which I'm providing if you're interested, but I don't expect you to memorize and use, is actually called anti-clinical eclipsed. So let's repeat that process, and we're going to take this back methyl group and then rotate it up into this open space right here. Again, our front carbon and the substituents on it haven't moved, so we can put those in relatively simply. And now this methyl group has moved into the space between this front hydrogen and this front methyl. So we'll take a line out, CH3. That puts one of our hydrogens in this space, and one of our hydrogens, back hydrogens, in that space. Now here, where we have two bulky groups that have a roughly 60-degree angle between them, right? This front group is about 60 degrees between it and this back group. This has its own name as well, while it is spelled G-A-U-C-H, it is pronounced gauche. Okay, so this is known as the gauche conformation, where two bulky groups have a 60-degree angle between them. We're going to do one more rotation, line up our two methyl groups. So here now our front methyl, one of our front hydrogens, our other front hydrogen, and now we've put our back methyl group lined up with our front, one of our back hydrogens lined up with our front, and our other back hydrogen lined up with our front. Similar to this anticlinical eclipsed, right? Even though nothing's perfectly aligned, by drawing our Newman projection in this fashion, it is implied that the carbon-carbon bond here and the carbon-carbon bond in the back, coming off of that back carbon up to that methyl, those are perfectly aligned in space, and the two methyl groups are also perfectly aligned in space. And same with the front and back hydrogen here, front and back hydrogen here. This particular conformation has a technical name of syn-periplanar. However, for our purposes, I would like you to call this totally eclipsed. Okay? So we have four unique conformations. What you should recognize is if I take this back carbon and rotate it again to put it into this open space, I've simply created a mirror image of this gauche conformation. If I continue that process, I'll see then my next rotation lining up with the methyl group with this front hydrogen gives me a mirror image of this eclipsed anticlinical conformation. And then finally, if I were to rotate it that back methyl once more, I would return to my anti-conformation. So we do have a total of 7 conformers that this goes through, but we only have 4 unique names to worry about. Now, these terms, anti-eclipsed, gauche, and totally eclipsed, those apply when we have two bulky groups, one on the front carbon and one on the back carbon, that are different than the other 4 substituents we need to concern ourselves with. Now, if all 6 substituents, the 3 on the front carbon and the 3 on the back carbon, were all the same, say for example that they're all hydrogen atoms or they're all methyl groups, we really only have 2 different conformations that we need to concern ourselves with. So I'm going to go ahead and draw those 2 over here using ethane as an example. So one of the conformations of ethane that we would be concerned with places each hydrogen atom in its own region of space. So there are the 3 hydrogens on my front carbon of ethane. Here are the 3 hydrogens on my back carbon of ethane. And in this case, we don't use the term gauche or anti to describe this. We use the term staggered. And we use that because all 6 of the groups that we're interested in, what their orientations are, they're all the same thing. I've used hydrogen here. These could all be methyl groups. They could all be ethyl groups. They could all be chlorines, right? The important thing is that every single one of these substituents is exactly the same as the others, right? And that way we can use the term staggered. Anytime we change that, we have to move into using these 4 terms here: anti, eclipsed, gauche, or totally eclipsed. The other possible conformation, and thus the other term we would use, places all of the substituents eclipsing each other again here. I'm just using 3 hydrogens front, 3 hydrogens back. And the term that we use for this situation is similar to what we had here. We would just call this eclipsed. 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 And that's because, unlike totally eclipsed and eclipsed, when we have different substituents, we really don't have any situation where we could have any different type of eclipsing interaction. So again, when all 6 substituents are the same, we use the terms staggered and we use the term eclipsed. So our ability to generate these different conformers by rotating around a single bond and using Newman projections to display them is the first step on the road to understanding how those different conformers relate to each other in terms of their potential energy. And we need to be conscious of both electrostatic and spatial interactions that are occurring within the molecule. And so these electrostatic and spatial interactions can be divided into 2 types of effects. We have one known as torsional effects, and the other is known as steric effects. Torsional effects are the word torsional effect or a torsional strain is used to describe what occurs when 2 bonds align with each other. So what does that mean? Let's go ahead and draw a Sawhorse and Newman projection for butane that would demonstrate torsional strain. So my Newman projection would need to have 2 bonds aligned with each other on different carbons. So I'm going to arbitrarily set my front methyl group. Wow. Let's try that again, huh? So here we have the circle. There's my front carbon. And I'm going to set a methyl group in the up position. I'm going to put a hydrogen, 1 of each hydrogen down here. And now I'm going to put a hydrogen here eclipsed by that methyl group. We'll put our back methyl group here. And finally, our last back hydrogen here. So this Newman projection, I'm going to now convert to a Sawhorse projection. Here is our front carbon. Here's our front carbon. I have my methyl group. Here's my back carbon. And now, since this hydrogen is aligned with my methyl group, that means all 4 of these are in the same plane. My methyl carbon, my central carbon, my third carbon, and finally this hydrogen coming off of it. I'm going to put in the other 2 substituents on my front carbon. I'll have a hydrogen coming out of the board towards you, and another one coming behind the board towards me. And now here on my back carbon, I will have a methyl group coming out of the board towards you, and a hydrogen coming behind the board towards me. So let's think about what's happening with this interaction between this carbon-carbon bond and this carbon-hydrogen bond. Our Newman projection tells us that they are aligned with each other in space. Now, each of these bonds is a pretty strong region of negative charge. We have 2 electrons in this bond, 2 electrons in this bond, so we have 2 negative charges that have aligned themselves in space. Vesper tells us that these things want to push away from each other. These similarly charged domains don't want to be close to each other, and that's true in terms of bonds being eclipsed. So this pressure that they're exerting on each other, trying to push each other away, is known as torsional strain. Another way to describe torsional strain, right, is repulsion due to the electrostatic forces in bonds wanting to be away from each other. Or torsional strain is caused by eclipsing bonds, right, which is a region of electron density trying to repel each other. We have two bonds that are eclipsed, they're pushing against each other, that introduces torsional strain. By introducing torsional strain, we have increased the potential energy of the overall molecule in this specific conformation. So torsional strain increases potential energy. I'm going to draw a slightly different conformer to demonstrate of butane to demonstrate the concept of sterics. So if instead of using the Newman projection we had, we can now produce, right, so this was our eclipsed. Let's now draw our totally eclipsed conformation of butane. So I'll draw my front carbon and its substituents first. And for totally eclipsed, I would have both of my methyl groups aligned and eclipsing each other, which puts both of these back hydrogens eclipsing the front hydrogens. Let's draw a sawhorse projection of this to see what's happening. Here are the two carbon atoms that define the bond I'm rotating around, carbons 2 and 3. Off my front carbon, there's my front methyl group, this one here. Off my back carbon, there's my back methyl group, this one here. And again, we have a hydrogen coming behind the board towards me, one coming out of the board towards you, and similarly here, one coming behind the board towards me, and one coming out of the board towards you. So in addition to the torsional strain in this conformation, because both of these carbon-carbon bonds are aligned and all of the carbon-hydrogen bonds are aligned, we have a new factor to consider. The size of this methyl group is quite large in comparison to the size of a hydrogen atom. In fact, it takes up a pretty big region of space, which is best demonstrated by drawing out those carbon-hydrogen bonds. And similarly, this methyl group is also going to take up a pretty big region of space if I draw out all three of my hydrogens. And so here now, this methyl group and this methyl group are competing for the physical space in this region. They're actually bumping into each other a little bit and getting in each other's way, right? And this introduces a new type of strain in the molecule known as steric strain. And steric strain is more accurately defined as a repulsive interaction or a repulsion caused by two bulky groups. Anything larger than a single hydrogen atom is a bulky group trying to occupy the same space. They can't, they're pushing against each other. This raises the internal potential energy of the molecule as well. And so torsional strain increases potential energy. Steric strain also increases potential energy. So we've looked here at two different types of eclipsing interactions, and we saw how torsional strain comes into play with our eclipsed. Both torsional and steric strain come into play with our totally eclipsed. Now let's take a look at our gauche conformation and staggered conformations to see, our gauche conformation, to see what's at play there. So for our gauche conformation of our molecule of butane, right, our Newman projection for that is going to look like this. Here's my front methyl group and my 2 front hydrogens. And there's my back methyl group and my 2 back hydrogens. And so what we see is that in this situation for a gauche conformation, we don't have any bonds that are eclipsing each other, so we have no torsional strain coming into play here. No torsional strain. However, we do still have 2 big bulky groups that are relatively close to each other, and while they're not as close to each other as they would be if we were in a totally eclipsed conformation, in the gauche conformation there is still a small amount of steric interaction between these 2 methyl groups, and so while we have no torsional strain, we do have some steric strain. Finally, let's take a look at the anti-conformation. In the anti-conformation, we place the 2 bulky groups completely opposite each other in the Newman projection. And so now our 2 methyl groups are completely opposite each other. Here again, we have no torsional strain. So this is our anti-conformation. We have no torsional strain. And because we never have 2 bulky groups near each other, front and back like we do here, we also have no steric strain. So now we've looked at the eclipsed, totally eclipsed, gauche, and anti-conformations at butane. And what I'd like to do is rank those based on their different potential energies. So our totally eclipsed conformation had both torsional and steric strain. If we then move down, we can also say that our eclipsed conformation, that no longer had steric strain, but it still had torsional strain. In our gauche conformation, which I'm going to abbreviate G, we only had steric strain and no torsional strain. And finally, in our anti-conformation, we had no strain at all. So we would expect that highest in energy is going to be, number 1, highest potential energy, the most strain, is going to be from our totally eclipsed conformation. Moving from there, the next lowest in energy would be our eclipsed conformation, and then our gauche conformation, and then finally lowest in energy is our anti-conformation. So highest potential energy, and now here anti are lowest potential energy. Remember that every time we introduce strain, that raises the potential energy of the molecule. And so now we can compare the relative energies of these different conformations, all for butane. The last thing we need to do is take all of these assessments that we made and represent it on a potential energy diagram. So next we're going to see how to do that. Potential energy diagrams are an incredibly useful tool for us in chemistry. They allow us to compare relative potential energies of different species, as we're going to do today in this video lecture. But later on in the semester, we're also going to see how we can use a potential energy diagram to describe the energy changes that are happening in a chemical reaction. For this video lecture, I'm going to limit my discussion of potential energy diagrams specifically to conformers, and then when we get to reaction chemistry, I'm then going to expand upon it in a later video lecture on how we use potential energy diagrams to talk about reactions and energy levels in reactions. And so, what are the basic features of a potential energy diagram? Or what would I look for if, what am I looking for when I ask you to produce a potential energy diagram? Well, we have to start off with two axes, a y-axis and an x-axis. Our y-axis is always relative potential energy. And the use of this word relative here is very important for our purposes. Even typically, I won't expect you to put numbers there, and if I want you to use number, I'll tell you all the numbers and what you should be doing with them. But generally speaking, we are qualitatively comparing two different states. We are not necessarily interested in the absolute energy differences or the absolute energy of a molecule. We are usually interested in what is this molecule's energy relative to another molecule's energy, or this conformer's energy relative to a different conformer's energy. For doing a potential energy diagram, right, for conformers or for really any situation, the top of this y-axis is our highest potential energy. So this is high potential energy up here, right? This corresponds to a system being less stable. I don't like using the word stable. I would think of this as higher potential energy, lots of strain, it's less happy. And the bottom of our y-axis is lower potential energy. The molecule is more happy, but we'll use the technical term more stable. Specifically for conformers, along the x-axis, what we're displaying is the dihedral angle, or the angle between a group on the front carbon and a group on the back carbon. And that angle between them is termed a torsional angle or a dihedral angle. Either term is completely correct. So we'll call it here our dihedral angle. Right? And now this gives us an opportunity to say, okay, with these different dihedral angles, what are their relative potential energies? And if you remember the list we made before, right, a very high energy system is totally eclipsed. Very low energy system would be anti. So because anti has the least amount of any kind of strain in it, it defines our 0 point in terms of relative energy. So I'm just going to go ahead and put a point right here. About the middle of my x-axis, I'm going to use an A to label that as my anti-conformation, and it's lowest in energy. Now, moving from an anti-conformation the next conformation rotating one of the two carbons would put me into our eclipsed conformation, right? So that eclipsed conformation is going to be higher in energy than my anti-conformation. So here now would be my eclipsed conformation. I'm using letters along my x-axis, but you could also put a dihedral angle with its number, or you could just draw a Newman projection under the point corresponding to that conformation. Moving forward from my eclipsed, for butane, placing a hydrogen and a methyl group right, eclipsing each other, the next conformation I get is a gauche conformation. Now a gauche conformation has some steric strain to it, right? It's not as high in energy as an eclipsed or a totally eclipsed, but it's higher in energy than an anti. So I'm going to go ahead, put it there, and I'm going to mark it as being my gauche conformation. And then finally, I know my highest energy conformation was the totally eclipsed. And that's the next conformation I come to as I go through from anti to eclipsed to gauche, and then finally my fourth one becomes totally eclipsed, which has both torsional and steric strain. So in that case, it would be higher in energy than my eclipsed, and then there's my totally eclipsed conformation. Now, I can rotate this the other direction as well, and what I'd find is I would have an eclipsed conformation and a gauche conformation, and finally another totally eclipsed conformation if I rotate in the opposite direction. And I'm going to go ahead and fill in my little energy points along with where I have the conformations marked. So here now I've got the relative energy. Anti is lowest in energy, gauche is the next lowest in energy, then up from there is our eclipsed, and finally up from there is our totally eclipsed. The last thing we need to do is we need to connect these points with a curve. We don't want to use sharp lines, right? To do this, we want to use a smooth curve that goes from one point to the next. So that would look like, I'm going to curve down, curve up, curve, wow. And it takes a little while to get good at these, so this is, again, definitely use erasers. We would curve down, curve up to our eclipsed, curve down to our gauche, and finally curve up to our totally eclipsed. This is by no means beautiful, right? I don't expect what you produce for me to be completely beautiful, but I do expect to see curves and not sharp points. So if you were to, what I'd like to see is what I've shown here in pink. If you were to connect these, right, on linear trajectories, the way I'm doing here in green, that would be incorrect. So the green, that's the sad way to connect our points, and the pink method, where we have smooth curves, is the happy way to connect our points. So you should definitely have smooth, rounded curves connecting the different points of your energy diagram, right? Again, the y-axis gives us highest potential energy to lowest potential energy, and because this is a relative potential energy diagram, we can define our lowest energy species, which is our anti-conformation, as 0, and everything else based off of that. We won't get into absolute energies. We will just be using relative energies both this semester and next semester. And again, if I give you numbers for something, I will put a scale on the on the y-axis, letting you know how to use those numbers. So I hope you've seen how we can go from understanding the concept of conformations, being that same molecule, same atom connectivity, all we're doing is rotating about a sigma bond. We can't rotate, remember, we can't rotate about pi bonds in a molecule. We can only rotate about sigma bonds. So anytime you see a double or triple bond, that's not a bond that can rotate, right? We can use two different methods to visually depict that rotation and the conformers that rotating around that bond would produce. Sawhorse projections, or far more preferably Newman projections, which is what we're going to use in this class to depict different conformations. We can use those Sawhorse and Newman projections and our understanding of steric strain and torsional strain to evaluate the relative potential energy levels of the different conformers we can produce. And finally, take all of that information and produce a relative potential energy diagram where we can quickly visually see what is the potential energy of the different conformers that a single molecule can produce. So remember, you can't take two different molecules and say that they're conformers of each other, right? You can only make conformers of a single molecule, just different states of rotation about a single bond. All right. Thank you very much for your time. And as always, if you have questions, please feel free to bring them in to lecture, office hours, conference, or make an appointment. Thank you very much and have a great day.